Good morning and welcome you all. Today we have a speaker from IIT Delhi, Professor Ritumoni Sarma. Uh, I'd like to introduce Ritumoni Sarma first. Professor Ritumoni Sarma, Department of Mathematics, IIT Delhi. He has been working in IIT Delhi since 2009 and previously in IIT Guwahati in various capacities from 2007 to 2009. His research interests are group theory, finite, Lie and algebraic groups, number theory, algebraic number theory, and continued fractions, coding theory, and cryptography. He has so far published 36 research articles in various international journals of repute and guided successfully 7 PhD students in various topics of research. He did his PhD from Tata Institute of Fundamental Research, TIFR, Mumbai, in 2004. After doing MSc from IIT Delhi and MPhil from Mumbai University. Currently, he teaches supervised PhD students apart from various BTech, MTech, and MSc projects and does research in his areas of interest, which includes mainly theoretical study, which may involve certain advanced computations. Now, first of all, I would like to thank Professor Ritumoni Sarma for accepting our invitations. And now I request Professor Bhesh Prasad to welcome Professor Ritumoni Sarma. Now I request Professor Ritumoni Sarma to deliver the today's talk.
Hello everyone. So since I'm asked to give the talk sitting here, so I'll do that. Okay. So these are on currently.
Mic is on, sir.
Mic. Okay, so this mathematics professor Tilpara Prasad Sharma asked me to give a talk, and the idea was that I talk on how to make mathematics interesting, and it was very short. So then I thought on this because my area of interest is not mathematics education, but I have interest on this. So then I came out with this title because it is slightly before how to make mathematics more interesting. I'll say a little in that topic also, but very little. So abstraction in mathematics. So mathematics without abstraction is not possible. So what we say that people who love mathematics, they find all topics of mathematics interesting. So now question is how to make mathematics interesting is actually for those, for example, in the school, it is a compulsory subject, so we have to make the topic interesting. And then how to make it. So that's a big topic of research, and I am not going to touch that topic because I don't think it is a very easy topic to deal with. So let us quickly see what we understand by school mathematics. Some topics, not all, like arithmetic. When we talk about arithmetic, then we immediately think of the integers, rational numbers, real numbers, etc., and the operations, the binary operations there, addition, multiplication. And continue, maybe you are not able to see the slides. So So arithmetic includes integers and operations and other numbers. And basic geometry, in school we learn straight lines, triangle, circles, and quadrilaterals, normally quadrilaterals, and that's all perhaps. Then we talk about coordinate geometry. And then mensuration and combinatorics, right? And one more, most important one, algebra. Okay, maybe, okay. Now I can't see myself, the full screen. Okay, so, okay.
Yes, it's coming.
It's coming. Okay, fine. Now this is better actually. So the natural numbers, if you see any language, their natural number is a part of it, because when you start talking, we say the one object, so a person like this, so up means the one person, some two, and the numbers are essential. So when they started, we don't know, but it's a part of it. But if you see the number one, we use for a bird, a pen, or the universe, a planet, so the same number one works. So one has no form, right? So it is an abstract object. And we never define what one is. We don't have to define. We understand. Then the abstraction of integers and rational numbers, perhaps same for many people, but certainly not for irrational numbers. What abstraction we have? In fact, integers and rational numbers, that the human brain process in a different way. So people find slightly more difficult the rational numbers than thinking of integers. So similarly, irrational numbers are much more difficult. Just some little discussion on this. So first evidence of irrational number was, when you see Euclid's work, that he shows that number 2, square root of 2 is not a rational number, and which we now study in the school. Kids can prove that root 2 is not a rational number. And Archimedes worked on the circumference of a circle, and that the ratio of circumference of a circle and the diameter is a constant, which we call pi, and which is an irrational number, and he perhaps didn't talk about irrationality of that number, but only in 18th century, people understood the number well, and Lambert gave a proper proof that pi is an irrational number. But in the school, we don't study irrationality of pi. We just say that it is an irrational number. And in fact, it is more than, there are two kinds of irrational numbers. Some irrational numbers are algebraic and some of them are not. We don't even talk about algebra, what numbers are algebraic, what are not. So that we study in higher mathematics. So the real numbers are actually quite abstract in the sense that we learned, how we have discovered them, right? So there are actually, in the school we don't learn what real numbers are actually. So in these directions there are several approaches. One approach is that the real rational numbers you understand well, and then a completion of rational number is with respect to some metric. So this is again a terminology which is not in the school, is the set of real numbers. And another approach is due to Dedekind, which is quite popular. So there is a concept of Dedekind cut, so which is very useful to understand real numbers, but we never introduce those things. So abstractions is there in the set of real numbers, although the numbers are real. So and with my experience, when we discuss with the students, the real numbers are very difficult objects. They find dealing with real numbers very difficult. So another approach which resolves the problem, that if we allow that any real number is something like an integer, decimal point, and then you write integers, like 1.5 is a real number, so which is 3 by 2. Then 1.1111, so it is a recurring but infinite decimal. But similarly, pi is one such which is non-recurring, infinite decimal. And so every real number is like that. Perhaps that description is the easiest one. Okay. And another one, so maybe I'll come to that now, that for most people, rational numbers are enough because they need to perform these 4 operations: addition, subtraction, multiplication, and division by a non-zero quantity. So therefore, the natural numbers, which are so natural, and then you apply these operations and you end with the set of real rational numbers. So, but for the first motivation of irrational numbers came from Pythagoras' theorem that for a right-angled triangle, the longest side, each square is the sum of the squares of the other 2 sides. So, and this is how we understand root 2, right? If I have the smaller sides to be equal to 1 for a right-angled triangle, I mean, this is actually isosceles right-angled triangle, and then the hypotenuse has length root 2, right? And this is our first motivation. Another motivation we give that you see that if radius is 1, then what is the circumference of a circle? So, which is not a rational number. So, it is an irrational number. So, the idea of presenting real numbers on a straight line is certainly one very extremely useful concept. So, we believe that the straight line, we have a straight line which is geometry, and you are plotting the numbers there on the straight line. So, for example, you fix some point to be 0 and then 1 at some other point, and then we have to supply other points on the straight line. And if you notice there, to do that process, you need something called distance, right? So, if you fix 1 and 0, then you know where to place 2, where to place half, where to place pi, right? So, distance plays a very important role, right? So, but we never, I mean, without saying that, we use it. And in Treatise of Algebra, in 1685, John Wallis, his work, one can find that he used currently the way we present real numbers on a straight line, it is there historically first time. And before that, Descartes also used this, but not in the current form, but perhaps in the past also people might have used this, presenting real numbers on a straight line. So now if I come to geometry, because we are presenting real numbers through a straight line, though, so we come to geometry, and for most of us, I think we believe that geometry is not an abstract concept. And geometric concepts are not very abstract. That's why we feel. But they are. If you see the Euclid's axioms, you'll see that they're not very straightforward. Okay? So he understood the depth of the concept that you have to introduce in a different way. So the abstraction he gave. So now if we ask what a point is, then is it something very small? I mean, that is how we think in the school, that point is something very small. Then if they know what is a molecule or an atom, that is a point is like an atom. So atom has dimension, right? Or molecule has a dimension. We talk about its radius or its volume and its mass, etc. But a point does not have any dimension. It does not have a length, right? I mean, we cannot talk about its, even if we don't know its size. So there is no size. We never ask this question about a point. So it is an abstract concept. And similarly, other concepts like straight line, plane, for example, straight line has length, it's infinite, and it has no thickness. Similarly, plane has no thickness. So, and in the school, what we learn in the geometry are either on a plane or in 3 dimension, at most 3 dimension. Because even if you don't do 3-dimensional geometry in the school, but we talked of volume of certain objects, certain geometric objects, like a volume of a cylinder, volume of a sphere, volume of a cone, or surface area of a cone. So these are 3-dimensional objects. So we certainly do 3 dimension there up to a great extent. But if to a school child, if you say that actually we need higher dimension, right? Nowadays, advanced ideas are also told to the students, maybe not taught, but we talk about relativity in the class that, okay, actually Einstein talked about 4 dimension, the universe is of 4 dimension. So then how to understand 4 dimension? And currently in string theory, people talk about higher dimension, like 29 dimension, and maybe more than that. So this dimensionality, how to understand? So the idea of coordinate geometry, that Cartesian coordinate system, is very helpful, because to understand plane geometry, we use 2 perpendicular lines and call those lines x-axis and y-axis. And then for higher dimension, like 3rd dimension, 3 dimension, what we have x, y, and z coordinate. I mean, straight lines and perpendicular to each other. And then for 4 dimension, what do we do? So what we do, we simply say that, okay, for 2 dimension, you had ordered pairs, x comma y, right? X comma y is equal to x prime comma y prime, if and only if x equal to x prime, y equal to y prime, and these x, y, these are real numbers. So for 4 dimension, we write a quadruple, right? It has got 4 components, and it's obvious now that for a higher dimension, we can talk of 10 dimension, n dimension, where n is any natural number. It will have n components, and each component is a real number. And 2 such n tuples are equal if and only if ith component of the first one is equal to the ith component of the second one. So this is how a point in n dimension. And then people talk about higher dimensional sphere, like in 4-dimensional sphere, which I have shown here, that summation xi square is equal to a constant, which is a positive real number, because sum of squares cannot be a negative quantity. So it has to be a positive. If it is 0, each xi will be 0. So if I want a proper sphere of whatever dimension, c has to be positive. So similarly, you can think of a cube, but cube stands for the word 3, right? When you say a cube, that means e to the power 3. So I should not say cube in higher dimension, but I'm saying analog of a cube. So analog of a cube in 4th dimension. So how many vertices will there be, right? So in actual cube, number of vertices is 4 plus 4, right? 8 of them. So how do you get them? Because you have 3 possibilities, x1, x2, x3, and then each xi can be, say, 0 or 1. Suppose I want the cube to have, 1 vertex at the origin, and other vertices, I mean, nearest ones are unit distance, like for example, 0, 0, 1, 1, 0, 0, and so on. Then I'll have for each xi 2 possibilities, 0 and 1, right? So therefore, I'll have exactly 2 times 2 times 2 times 2, that which is 8. So these are 8 vertices for a cube. For a 4-dimensional cube, you will have for each component 2 possibilities. So total number of vertices will be 2 to the power 4, so 16. So this way we have to do abstractly how how many vertices will there be. Similarly, how many faces will there be? So can we talk about face? Because in a cube, you have face, right? So a face is a planar thing. It is on a plane. Every face is on a part of a plane. But if I am in 4 dimension, what is that? What we should talk about? So it will be a hyperplane. It is something which is 3-dimensional. So it will be more complicated. So, but it is there. People study those also. Okay, I'll not talk more on this. I'll go to the next thing. So, in the direction of abstraction, so there is a quotation which I have taken from internet. Abstraction in mathematics is the process of extracting underlying structures of something. What is that? Patterns or properties of mathematical concept, removing any dependence on the real world objects. So you are not supposed to keep yourself attached to the real world objects. Your concept, the abstraction is such that it is detached from there, and it should not depend on the real world object. And after that, with which it might originally have connected, and generalizing it so that it has wide applications or matching among other abstract descriptions of equivalent phenomena. So there may be equivalent phenomena. So what abstract concept you develop, it will it can be used for various real world phenomena. So it need not be only related to one thing. For example, what we have in college, for example, abelian groups, or maybe vector spaces. Vector spaces may be easier to say. So vector space, the concept of vector spaces is an abstraction of Rn. So what we are talking about, n-dimensional real space. So what is R? It is a straight line. R2 is a plane. R3 is the space, and R4, I don't describe geometrically what it is. So we say that it is 4-dimensional space. Similarly, n-dimensional space. So vector space is a generalization of this concept of space. And then I'll talk slightly more about it in the coming slides. That why just we can talk about real space. You can have complex space or not. Can you have some other kinds of space? So answer is yes. You have it. So, and it is useful. It is, if you see, when you use technology, for technology, when you use computer, and in the computer, everything is limited, everything is finite. So real numbers has got infinitely many points. So computer and real numbers, maybe there is a problem. So maybe we can have something, a replacement of the set of real numbers. Maybe we have several replacements depending upon what real problem you have to deal with. Okay, so therefore this abstraction is actually helping us to solve certain real world problems. So I'll come back to this maybe after some slides. So because this quotation you can read. I don't have to read everything from here. And so to be abstract is to remove context and application. So where abstraction is concerned, you don't worry about context and application. But practically, what we have seen that such abstractions actually is helping us in solving some other problem, real problems. Okay, so that is not the desire for abstraction. Okay, but it is an advantage. So let me now talk about another topic which is very basic. In the school, I believe even nowadays it is done. Set theory is taught in the school. So,
11th class.
Okay, it is in the 11th class. So I used to be in the high school. I don't know whether it was in NCERT. So set theory, we don't put much effort to define what set is, but historically it is an extraordinary idea, really. Dedekind and George Cantor, they worked on set theory and they introduced the concept of sets. And maybe, see, such historical statements are not kind of 100% correct. There may be other people who might have thought of or introduced these kind of concepts. But these people are considered to be the first people. But in 20th century, in the beginning of 20th century, Bertrand Russell pointed out certain drawbacks of these concepts. And in this direction, Bertrand Russell's paradox is well known. He has several paradox related to set theory I am talking about. He has a paradox for probability theory also. So he has multiple kind of talent. Russell got a Nobel Prize for, excuse me. He got Nobel Prize for literature. He was a mathematician, and he was one of those in the beginning who understood relativity when Einstein proposed relativity. I mean, people used to say that only 4 people understood relativity. He was one of them. And in fact, Russell has a book. He has written book on ABC of relativity is one book he wrote, and there may be many more. I'm not aware of all of them, but I don't remember all. But he's one who have done a lot of work in mathematics. And in fact, foundation of mathematics, he has written books on foundation of mathematics. He has written books on some literature, religion, philosophy, and many other things. So anyway, so this is just praising him. But important thing is that the set theory proposed by Dirichlet, according to this concept, what the previous, prior to Russell, all sets, if you collect all sets, that collection, is it a set? That's what Russell asked. And according to the definition, set collection of all sets is a set. Then what he did, he called this set as Z. I mean, he might have used a different notation, I don't remember, but he said, call it Z. Z is the collection of all sets. And since it is the collection of all sets, and according to the concept of Dirichlet, Z is also a set, so Z must contain itself as a member, right? It contains all sets, and since Z is a set, it contains itself as a member. So there are examples of sets which contains itself as a member. So he then divided Z into 2 parts. Those, you can see X, which contains those members of Z, which contains itself as a member. See that? A is in A, mathematical notation. And those Y, those sets which does not contain itself as a member. For example, the set of natural numbers, elements are numbers. N does not contain N itself as a member, right? But the way this partitioning is happening, that X and Y are disjoint, right? X intersection Y. If A is in A, then I'm sure that A is not containing A, right? By definition, X and Y are disjoint. And every member of Z is either in X or in Y, right? So these are the things I have written here, that every member is, Z is equal to X union Y, means every member is either in X or in Y, and X and Y are disjoint. And none of this is empty, because Z is a member of X, because Z contains itself. So Z must be in X. Similarly, N must be in Y, because N does not contain itself as a member. So then Russell asked the following question: where will you put Y? Y is a set according to Dirichet's theory. Where will you put Y? Which part of Z? Y belongs to X, or Y belongs to itself, Y? Okay, this is what the question is. If you have noticed this definition of X and Y, let us see, can Y be in X? If you place Y in X, what will go wrong? Y must be in Y also. If Y is in X, then what property it should have? It contains itself. But if it is in Y also, then X intersection Y is empty, will fail. Right? So therefore that is not possible. So Y cannot be in X. If Y is in Y, then Y must be in X also, because it is satisfying the property of elements belonging to y, x. If y is in y, then y must be in x. Again, the same problem. X and y are disjoint, so therefore that's not possible. So therefore, it's not possible to place y anywhere. So this is what is Russell's paradox is. So it means there is a problem in abstracting in the concept of sets. So that means you have to formalize in a different way. The way it has been happening is not correct, right? So what we learn in the school, just we say that, okay, it is a collection of well-defined objects. So this well-defined, what does it mean, is a deep concept, which we never tell students, which perhaps most of us have not studied also. So that's okay. But I'm saying to be correct, to be perfect is important in mathematics. You cannot have loopholes. Okay? We need a foolproof definition of every concept. It may be very long. To define a concept, you may need several pages. That's okay. For example, for set theory, maybe you need a booklet. But we have to do it correctly. But it was done. And Russell was one of them who's considered to be one of the kind of pioneer in this direction. Okay. So next, I come to the concept of distance. So I have already told you that when you plot numbers, real numbers, on a straight line, we, without paying much attention, we just use the concept of distance. Because once we plot 0 and 1, we are forced to plot other integers, other numbers, right? That is there. So distance, when we talk about distance between two real numbers, it is the absolute difference. We find their difference, right? Like, for example, distance of 5 and 7 is 2. So we first find the difference. We subtract one from the other. If it is negative, we remove the minus sign. So it is the absolute difference. So abstraction of distance, how do you do? So we don't worry about what is distance in R. So we'll try to extract what are the properties that we expect that what we call distance. If we have, suppose we have an abstract set, then given any 2 points, you need to give a non-negative number. So distance is a non-negative quantity, right? Distance between any 2 points. So now your set is not the set of real numbers, right? It is some set. So distance should be non-negative. It must be 0 if distance is from a point to itself. Distance of my distance from myself should be 0, right? And if distance of one person from another cannot be negative. It is a non-negative quantity. It must be positive that 2 points are different. And distance between A and B and B and A must be same. Whether you measure from A to B or B to A, these two quantities should be same, which is symmetricity. And the third one, the last one actually, whether you call third or fourth, and that it is a triangle inequality. That if you have 3 points, A, B, and C, then distance between A and B should not be more than distance between than the sum of the distance between A and C and B. So in a triangle, we know the sum of two sides is not less than the size of the third side. So these properties are expected. So and they actually work. So then let me now quickly say a slightly surprising thing. There is a concept of p-adic numbers. You might have seen before. Let me talk about 2-adic. Given any prime p, there is a concept of p-adic numbers. P-adic distance. So for p equal to 2, the first prime, 2-adic distance. What is the 2-adic distance of 0 from 2 to the power n? So 2 to the power n, when, for example, 2 to the power 4 is 16. So what is the distance of 0 and 16? So according to the definition of 2-adic distance, it is half to the power 4. So distance between 0 and 2 to the power n is half to the power n. I'll define again, but I'm saying this is how it is. Okay, so because your general question will be what is the distance between m and n, where m and n are two integers. What is the two-adic distance? Yes, we have a formula. We'll talk about it later. So if you believe that this distance, whatever two-adic distance is, satisfies all the above properties, these 4 or 5 properties, it is verifiable, very easy to verify. Actually, it is. Then let us see the last equation here. 1 plus 2 square and so on. So it is a series. It is an infinite series, right? So for a moment, if I look at the partial sum, that sum from 1 to 2 to the power n, okay, that sum is a sum of numbers. So this sum is equal to, because it is in geometric progression, 2 to the power n plus 1 minus 1, right? If I add 1, 2, dot, 2 to the power n, outcome is 2 to the power n plus 1 minus 1. Now, this is the partial sum. Now, let us go back here. So, when n is approaching infinity, 2 to the power n is approaching 0 according to two-adic distance. Why? Because distance between 2 to the power n and 0 is half to the power n. Because half to the power n is approaching 0, right? Half, 1 by 4, 1 by 8, 1 by 16, 1 by 32, 1 by 64, and so on. So it is a positive real number which is converging to 0. So that means what is happening in the series should converge to according to two-adic distance, the series should converge to what? Because my expression is 2 to the power n plus 1 minus 1, right? So 2 to the power n plus 1 is approaching to 0, right? So therefore, the series will converge to minus 1 according to two-adic distance. So this equality will hold. So this series converges to minus 1. Okay, so this is not the real number equality. This is not an equality of real numbers. Of course, left hand side are integers, okay, but you are not inside the set of real numbers. You are somewhere else, okay. So don't say that this equality holds in the set of real numbers. This is false in the set of real numbers, because when you plot using two-adic distance, if you want to plot integers, you are going to put 0, then say 1. After fixing these 2, where will you put half? Where will you put 2? You are going to put 2 closer to 0, because 2 is nearer to 0 than 1. Distance of 1 is 1. Distance of 2 according to two-adic distance is half. So I have written the general expression. Distance of 0 and 2 to the power n is half to the power n. So distance of 0 and 2 is half. So therefore 2 will be put in between 0 and 1. Okay. So this is not the real line. This is something else. Okay. In mathematics it is called Q2. I mean the real numbers will be replaced by something called Q2. So which I will not go into. I will not discuss that. But I am trying to say that because of abstraction of distance, we got two-adic distance, and then we got a different mathematics, which is not the real mathematics, which is not done in the school. It is not expected to be done in the school. But in the advanced level, such a thing is happening. Okay? So I wanted to show you that how abstract things are there and which are quite abstract. Starting from the numbers, and we have got, with a minor change, we have got something very different from what we believe. Again, if I come back to the real numbers, for real numbers, this equality is obvious, not because you know geometric series. I know because of geometric series, you can write it as the partial sum will be 1 minus half to the power n plus 1 divided by half, right? This is according to the formula. And when I take n going to infinity, and it converges to 1. So that is okay. But if you think that for this equality, without bothering about distance, I mean, I'm going to cheat a little bit, that you think of that you have some object and you have divided into equal halves. So you take one half in one place, and from the remaining part, you again divide it into two equal parts, which is 1/4, which is half square. So that remaining half you put again there, and this way, whatever is remaining, you divide into two equal parts, and then collect. So you keep doing this, and this way you get back the original object, right? So this is how one can explain in the school, right? So this is okay that to explain in the school like this, people like it, but we must tell students that for an infinite series, distance is important, because when we say that this equality holds, it means that partial sum, if you allow me to call it Sn, the sum of the first n terms converges to 1. And for convergence, you need distance. So this is for class 11, 12, not for high school. So there we don't have infinite series. So the distance is there, and in the school, everywhere what distance we use is called the Euclidean distance. Euclidean distance. So Euclidean, we are most used to Euclidean distance. Just to again repeat what is the meaning of two-adic distance, I just quickly tell the definition here, that if you have two integers, x and y, you subtract x minus y and take the absolute value. So you can always write an integer that what is the exact number of times 2 divides it, which is 2 to the power r. So 2 to the power r divides x minus y, but 2 to the power r plus 1 does not, times s, where s is an integer not divisible by 2, right? Then distance of 0 from this one, which is half to the power r, is the distance of x from y. So this is called two-adic distance. Similarly, one can do it for any prime. Okay, so this is just to people who may be interested. Okay. Okay, so in the college level, abstract objects are introduced suddenly, and this, for example, group theory, groups, then rings, metric spaces, topological spaces, etc. So perhaps nowadays topological spaces are introduced later, may not be in BSc level. Kronecker once said in some meeting, mathematical meeting, so in 1886, he said, natural numbers are created by God and everything else is a work of men. So perhaps he is referring to only mathematical work. So God gave us the numbers. As I have said, that natural numbers are part of our language, but other things we have, in natural numbers we don't have to define them, but other concepts we need to define. Even set we have to define, right? So in other words, the abstract concepts of mathematics, except the natural numbers, are a creation of human. And there are more quotations which will come soon. So, but what are the advantages of doing that? Which I have already given hint that for certain things which are, some people wrote what the abstract concept is, and later people utilized that abstract concept to do solve some real world problems. So this kind of thing is anyway there. So, but in what mathematicians believe, that the abstract concepts reveal deep connections between different areas of mathematics. That is one thing. And since there is a connection between two different areas, one area results from one area may be helpful to guess what may be certain facts about a different area of mathematics. And techniques and methods of one area of mathematics may be helpful to solve problems in other area. So some different people of different area interact, and then they find a new way of solving problems. So which is collaboration. And in the conferences, people attend lectures of different area of mathematics. So it is a good idea to attend lectures of others' lectures, which may not be of your interest. So, so I'll not read all of this. But what I'll say another statement due to Russell. I'm a fan of Russell as such, mathematically. Ordinary language that what we speak actually are completely useless to describe the work of physicists. That's what he said. But then he said, however, mathematics and mathematical concepts are helpful for them to say, but that is also not enough. So that means we do not have enough abstraction of concepts. Maybe we need more of it. So what I have understood from his quotation. So in other words, abstraction is also essential to understand the real world, to understand the universe. Abstraction in mathematics is very useful because you understand. Understanding the universe is a work of physics. Physics people study universe, whether whether it is an atom, molecule, or boson, whatever it is, very small, to whether it is a planet, solar system, universe, and whatever. So everything physicists study, right? So what Russell said more than 100 years back, not more than 100 years back, that is about 100 years back, that maybe we need more of abstraction of mathematics. So we cannot avoid, we cannot get rid of it. So now, small thing, but very important, that the concept of a field is something which is introduced in the college level, but in the school already we have been using this set of rational numbers. We know that we can multiply, we can add, we can multiply, we can subtract, we can divide by non-zero quantity, and that's what a field is. Addition and multiplication are commutative and associative, and multiplication distributes over addition. So those properties are there in Q. These are naturally happening. So only thing is abstract. We have to say that you think of an object where all those properties hold, right? So those properties are true for the set of real numbers, true for the set of complex numbers. Then can we think of any other set where such a thing is happening? So one example I'll just bring here. So the last paragraph here, that the even numbers, even integers, can be thought as zero. We can call it zero. Zero is the even numbers, okay, whatever even is. And one, the odd numbers, all integers. Then the general concept, even school students understand, that if I add two odd numbers, I get even. So that means if I add 1 with 1, I'm supposed to get 0. Okay, these are my elements, even, odd. These are my elements in the set, just two elements. I want to add even with odd with itself, even with itself. So these are the four things I have to do. Similarly, I have to multiply. So whatever addition and multiplication we know about even and odds, we just apply that. So therefore, we have got two operations on the set of 0 and 1. So these 0 and 1 are not the integers. 0 stands for even, 1 stands for odd. Okay? And this is the smallest field, binary field, also denoted by F2. Also people call Z modulo 2. Okay? But the simple introduction of even odd is helpful to explain students. Even school students understand that. I have tried it on students. So they were very happy to see this one. And so this is a field, and this is the smallest, and is a finite field, because where what we have Q, R, and C, these are infinite. So I told you that finite fields are useful, and therefore, because you have finite field, now we can think of, if you allow me to call it as F, which has got just two elements, I can think of Fn instead of Rn. You see that? Fn. As you know, so 0, 1, binary numbers are very useful in electrical engineering, computer science, right? So the abstraction of Rn into vector spaces and R into field, and then from field getting a finite object of similar type is quite interesting and also helpful now. Okay, so I'm trying to say that abstraction is also helping us to discover new things, not just helping in understanding other area of mathematics and so on. I'm saying it is helping in solving problems, real problems. So again, the middle paragraph here, that system of linear equations which is introduced in the school itself. Two equations in x and y, both linear, and then we teach them various methods. To start with, they draw straight lines on the graph. Two lines they draw, check whether they are parallel. If not parallel, they will intersect, and find a point of intersection. Then we say that the point of intersection is the solution, right? But then we have to be, in the real world, the questions, number of equations may be very large. Number of unknowns may be very large. Why just two equations and two unknowns, right? So therefore, we cannot get rid of this abstraction. To solve real problems, we need to do more abstract, right? So we have to deal with more abstract situation. So more generally, after school, what we teach them is how to deal with a system of linear equations. So number of unknowns may be some n may be 100, and number of equations may be m, that may be again very large. Okay, so that may be very large. So then we introduce a presentation of the system of equation as Ax equal to B, where A is an m by n matrix, x is the column of unknowns, and equal to B. B stands for a column of constants. And whatever theory is developed, this theory is applicable for when A and B are matrices with coefficients from Q, then you will get solutions from Q. I mean, you may not get, but your theory will say whether you will get it or not. It is a foolproof theory. And same thing is applicable for reals or complex, and interestingly and obviously that the same theory works for a finite field. So therefore, abstraction is helping. You just do once, it works for all. So so the last remark, so that it is very important to present mathematics to our students in an interesting way. It is really important what many math educationists do, that how to present mathematics in an interesting way. But what is interesting for me may not be interesting for another person. So again, that is they do that thing also. That is very good. But I have not done much, but I have seen people doing that. So often people do present an abstract concept partially, because if I have to do everything, it becomes very difficult, and people are discouraged to see that. So it will no more be interesting, perhaps, for many people. But a special case may be although may be very motivating, but it will remain incomplete. So therefore, wherever it is possible, try to do as much as possible. And enough number of examples and variety of examples must be provided. That is a very important thing to do, so that the abstract concept can be explained properly, and the depth of abstraction is there in those examples. So examples should actually be very illustrative. So, and we must realize in mathematics that there are layers of abstraction. In my discussion also, I started with numbers, then we go to a higher difficulty level will be there, and abstraction will be one layer of abstraction, then another layer of abstraction. So integers, then rational numbers, real numbers, then field, then maybe more. Okay, so there are layers of abstraction. So if you go higher and higher, new layers will be there. So it is there, we cannot avoid. So, so as a result, things becomes really difficult, I agree, but at the same time, it is essential. So I'll conclude here. Thank you for your attention. And thanks, Professor Dilprasad Sharma, for inviting me for this talk. And thank you, everyone. Yeah, sure.
Any questions?
Your presentation very attractive and very informative. You have said also that the point and the line, there is no width. So I want to know, sir, if 0 is I think 100 times when we represent 0. So how is the point make a line? So sir, scholars say
Yeah, it's a very good question. Yeah, it's a very good question. Yeah. So when I was writing, that also came to my mind. So people might think of this one. So yeah. So if you
because we say that circuit is the initial point. When 0 move there, then line formate, and when line formate, then we line the space to x and y dimension.
right.
So, sir, from here we have some doubts in this reality and basics of these things.
Right. I understand what your question is. So, so even if we have, so there is the notion of convergence is there, right? So that convergence is for only countable many terms, right? So even if you add 0 countably many times, I mean you will get points. So countably many points. So then finitely many or countably many even will not do what you are asking, that you cannot get a line. So then you need uncountably many things. So uncountable infinity is something again a different concept. So your idea is to, if 0 plus 0 is 0, so you are saying if you add 0 any number of times, finitely many, you get 0. If you 0 countably many times, you will get 0. But how about if you add uncountably many? Can you add uncountably many times? So there is no such concept. There is no such concept. What you believe that you can add 0 uncountably many times. So 0 is fine still, but for a positive quantity, I mean uncountably thing we have don't have. So convergence concept is for only countability. So another thing, so your question perhaps is related to measure theory. So if you have heard of measure theory, yeah. So single point measure may be 0. Counting measure is 1, and if it is finite set, the counting measure will be the exactly number of points. But whereas on infinite thing, if you allow a single point to have some measure, however small it is, some positive quantity, then any infinite set will have measure infinity. Right?
Yes.
So it's comparing this to is not the right thing to do actually.
Oh, yes.
It's not the right thing to do.
Right.
Okay. So,
Okay.
but it's a really very good question.
Yes.
So,
Thank you, sir. Thank you.
Good morning, sir. You talk about the layer of abstraction in mathematics, and simultaneously you mentioned that you give some sufficient example about the abstraction. So sometimes I face the problem in school education because I have some abstract concept, but we are not able to relate some practical example or sufficient example to provide the student.
no, I do agree. It's not always easy to find examples. I mean, currently, most abstract theory of mathematics is something called category theory. So then they just deal with using the properties and then giving example, and sometimes they rarely find examples. that we agree. I don't know exactly what kind of concept you are facing difficulty. I don't promise that I will be able to solve your problem, but I do agree.
No, but sometimes student also give some practical example. For the example, suppose sometimes I mentioned that coding theory and etc. all these things. I explained that this is the application of cryptology and etc. all these things. But again, student asking that, sir, it is not visible. Yeah, it is not visible around us. So this is the problem area in mathematics about abstraction. That things I face as a teacher, especially in the school education.
Yeah. I can say that I just agree to that. It's not always possible.
Thank you, sir. Thank you.
But we should, I'm saying that we should try to give as much as possible. Yeah. And nothing is enough anyways. Right?
Okay, thank you. Thank you.
Yeah.
Limitation of our personal affairs.
Yes. That is one.
So limitation is always there.
It is there. Yeah. So that's why it is an area of research. Yeah. Oh, yes.
Sir, thank you for this. We have a doubt. Setting your presentation that abstract, they are called real. You gave an example of 1.5 being a real number. So can 1.5 be really presented as an abstract number to school students? What is your opinion?
Question.
Sorry, sir?
I didn't get your question.
I said you quoted that real numbers are abstract, though they are called real, and you said that 1.5 is also a real number, right? So can 1.5 be presented as an abstract concept to school students?
No, I don't want to present anything to the abstract to the school students to start with. But I'm saying that whether you talk about the number 1, 2, 3, integers, or any other number, those are abstract concepts, first of all, that we should realize. But when I'm telling students, first of all, natural numbers, we never tell them that, okay, what is 1? We don't have to, right? Just we tell them 1, 2, 3 like this. If we add 1 with it, 1, we get 2. And you add 1 with n, you get the next number. So write that, like that. But what I'm trying to say here, that gradually we increase the abstraction, that the process of division gives us a rational number. So 3 divided by 2 gives you 1.5. So this is slightly abstract, more abstract than in natural numbers. I mean, such a comparison is fair or not, I don't really know, but that is my personal feeling. But then, beyond rational numbers, if you try to understand, historically also if you see, that square root of 2 is an irrational number was proved, I mean, long back, before 300, I mean, about 300 BC, but about pi, the whole theory was there. I mean, there is a formula for writing what is the length of the circumference if you know the radius. But at the time, approximate value of pi was given. I mean, not just 22/7, some other also. I mean, people always try to find what is the better one. And it was in 18th century, people proved, somebody, Gilbert, I mean, what is his name? Lambert proved that it is an irrational number. And so, and then another thing is like, what are all real numbers? There is no form as such, right? With the help of the real line, we say that between any 2 points there is one real number. If you give me 2 real numbers, I will be able to produce infinitely many in between, right? There is a way to do that. If you give me a and b, then a plus b upon 2. If a and b are different, upon 2. I asked my BTech students who have perhaps stopped in their JEE exam, but tell me a number in between. So then initially many people find it difficult to give a number in between. So, but just simply take average, or you can multiply 2a plus b upon 3 also will do. So this way infinitely many of them are there, of course. But these are not all, there are still more. So then historically again, to give a proper description of real numbers took a lot of time. So Dedekind was one such who gave the concept which we call Dedekind curve. And similarly other concepts are there. If you see what real numbers are, to do advanced calculus, so real numbers are presented with some properties. For example, least upper bound property and so on, right? So there are various ways of approaching it, and then you certainly realize that real numbers are really abstract. So they're real. I mean, whatever you want to call real, that's fine. Okay.
Thank you, sir.
Have I answered your question?
Yes.
Okay.
So let us, I think there is no more questions. Let us thank the speakers. A round of applause.
Okay. Thank you.
Now there is some announcement. We'll have this parallel session 202, room number 202 here only, 207, and online like a conference room, boardroom. And those who have not filled the TA form and others, please fill and please sign the online form and please write the bank details properly so that it can reach your account. Otherwise, it will remain in between. Right? So these are small amount, and we'll have maybe if we finish the session, we'll have the validity program. We'll announce it in the afternoon, maybe after lunch or around 2:30. We are planning. So thank you very much, and we'll now break for cup of tea. Before that, we can have a